So good afternoon, everybody, and a very warm welcome to this afternoon's webinar. My name's Claire Barris. I'm part of the ARCHER training team here at EPCC, and I'm very pleased to introduce to you Harvey Richardson, part of the Cray Centre of Excellence, who works here beside EPCC, providing us a great deal of support with ARCHER. And this afternoon, he's going to be talking to us about the new Cray Compilation Environment and also give us an update on the latest Fortran. So thank you, Harvey, and over to you.
So thanks, Claire. So as you said, I'm Harvey Richardson from the Cray Centre of Excellence for ARCHER. And I want to accomplish a couple of things in this webinar. So it's been a long time since we've done a webinar on a couple of topics. We've had a couple of previous webinars looking at the programming environment and how that's been updated on the ARCHER system. And I've also done a couple on features in Fortran Standards and how those have fed into the Cray compilers. And I thought it'd be nice at this point to do both of those, but in quite a constrained way. So what I'm going to do is describe something about the latest developer compilation environment that you would have on a Cray XC system today. Now there's a bit of complexity with ARCHER because the environment's a bit behind, and I'll explain that. And this will give you some hints as to some things you might see on ARCHER2, but this isn't intended to be in any way an introduction to ARCHER2, just to be clear. And the other thing I'll do is once I've done that introduction, give you a feel for some of the things that you're likely to see, then I'll concentrate more on how have the Cray Fortran compilers developed in terms of supporting the latest features, specifically from Fortran 2018. And I should mention that some of the slides here were also developed by Anton Sternlicht, who works within the benchmarking group at Cray, or now HPE. So he contributed to some of the Fortran slides. So just to reiterate, my plan is to talk a little bit about the current programming environment status on ARCHER, and then give you a feel for how that might change. So on the future systems, what might you see that's different from what you see on ARCHER today? And this is also true if you move to a system that you have access to that's running a more recent version of CLE than ARCHER does. And then in the second section, I'll talk about Fortran specifically. So if we think about the programming environment, this has been stable for a long time on ARCHER, and it includes a range of things relevant to developers. So it includes compilers, it includes message passing MPI implementation, it includes PGAS languages, it includes tools to support debugging, performance tools. It has a module setup that allows you to choose different parts of that environment. So you can choose to use, say, the Intel compiler rather than the Cray compiler, and scientific libraries. So this is bundled as a package, and sometimes we call that programming environment. Sometimes we use the term compilation and development. So CDT is another term that you might hear used. And these updates to this environment is generally released at most once a month. Sometimes there's a couple of months or 3 months between releases, but there's typically quite a large number of releases per year. And historically, what we've done is chosen particular of those releases to install on the ARCHER service. And then we've done some testing before doing that, typically done by the CSE team at EPCC. And then later on, the module defaults might change so that you as a user would automatically pick up a new programming environment. But you'd get some time to play around with that before the module defaults changed. And those changes would, of course, be announced in advance. So the current programming environment on ARCHER dates from 2017, and it provides version 8.5 of the CCE compiler. So CCE 858 and the MPI, which comes from a package called Cray MPitch, version 755. Now there is a more recent environment, which is not the default, that's available, and this is from December 2018, and that provides the 8.7 version of the compiler, so 8.7.7, and a more recent Cray MPitch. And in order to use that environment, there's a module that helps you to basically load a consistent set of software. So as well as the compiler, you'd have to change other things like MPI and libsci if you're using that. So there's a helper module called CDT, and CDT 1812 would get you that more recent compiler. And notice that I've gone from talking about an 8.5 compiler to an 8.7. So there is another CDT module that takes you forward to an 8.6 compiler environment. And And I've previously talked about what the differences are between those environments, both in kind of message passing support and in compilers in previous webinars. So one of the previous ones, we talked a little bit about the features coming in at the time in the 8.7 compilers. And as I said, the environment stayed static for quite some time on Archer, mainly because we decided not to upgrade the OS because of the time it was going to take. So that's the CLE OS environment that runs on Archer, and that has consequences for the programming environment that can be supported. So the programming environment's been static for some time. So this is why Archer itself is behind the current programming environment released by Cray, which of course is closer to what will happen with Archer2. So I'm going to describe a little bit about the differences between the current environment on Archer and the current shipping environment from Cray, which you should be interested in. So here's a diagrammatic view of the programming environment. So a range of programming languages on the left, and you'll notice Python and R here. So this is an example of part of the programming environment that's not available today. But if you moved to a machine that was running CLE6, an XC system elsewhere, it's likely to have that. And certainly it's something that this environment will carry forward into the ARCHER2 system. So a Python implementation supported within the Cray environment will be available, as will be an R implementation. So the other things you'll recognize, so you recognize MPI and SHMEM, you'll recognize OpenMP support, and OpenMP and OpenAC support for GPUs. So Archer currently doesn't have GPUs in it, but the programming environment does support programming with GPUs. And Cray has really been a proponent of the directive-based approach to do that. CUDA as well, the PGAS languages, so UPC, Fortran coarrays, support for global arrays. Then the environment that allows you to use those different compilers and get a consistent environment. So that's managed by modules, and in particular a high-level prog-env module, a range of scientific libraries. Another thing you might not be aware of is that there is software aimed at machine learning, and that software is not currently available on Archer. So that's another piece of the programming environment that you wouldn't be familiar with. And that comes with a plugin that optimizes, the performance of TensorFlow, for example. You'll be familiar with NetCDF and HDF5. Now the tools will change. So one thing that's future looking on this slide is that there'll be support for environments like SPAC and EasyBuild. So a lot of people are interested in using those tools to build quite large scientific applications with. So there will be some integration between the Cray programming environment and tools like those, which I know some people will be interested in. And then the range of tools that support debugging at scale. So you have GDB for HPC, which is a command line debugging tool, and then support to integrate with TiltaView and DDT. And the other thing to mention here is that although Archer runs PBS Pro, the programming environment does support Slurm as well as an alternative. And there are some systems around Europe that use Slurm as opposed to PBS Pro. So you'll get the idea here that some things you can expect are Python and R to be added to the environment you're used to, and some enablement tools that enable us to help build applications with SPAC and EasyBuild. So if I look at the current shipping environment, so we previously looked at what was on Archer. So the current shipping environment is from December 2019, and the next release will be this month. And that's available for XC platforms, so those are the Aries XC platforms like Archer, for ARM architectures, which, for example, GW4 has an ARM system, and more like traditional clustered solutions. And that current environment now has the CCE 9 compiler on it. So that's a major release beyond the 8.7, which is available on Archer if you swap the modules, and a newer MPI, and of course the other things have all been updated since then. And the packages I mentioned, the package is called Cray R, and there's a package Cray Python. So those two packages specifically, R is version 3.6.1, and there are Python 2 and 3 packages. So these include Python, NumPy, SciPy, MPI for Py, and Dask. So Dask is a tasking framework, if you're not familiar with what that is. And these libraries link to Cray libsci, and they take note of what OMP num threads is set to give you threaded parallelism as well. So that I mean, that's quite nice to give you a supported Python environment. And I know that EPCC has provided, an environment they've built for Archer users already. So I should say something about CCE 9. So because there's a major change here that's quite important for you, particularly if you're a C user. So this was released in August 2019, and the laws are not compatible with the existing software. So you have to switch a whole load of libraries if you use the default compiler that comes with this. So the CCE9 compiler. The default linking mode has been set to dynamic, so that's set to static on Archer. Now that doesn't mean that you have to link everything dynamically, but typically it's likely moving forward that some system libraries will have to be linked dynamically. But you could still build application libraries statically, and it may still be possible to build some applications statically, and you can switch your default to be static with an environment variable. But one big change here is that the CCE9 C and C++ compilers are now based on Clang. So Clang is a C language family front end for LLVM. So there's been a complete change here. And just so that it's not too confusing, the traditional CCE compilers have been termed classic. Now both are available at CCE9. So the default compiler is a Clang-based one, but you can switch modules to get back the classic one. It'll look and feel like the compiler you've currently been using. And Fortran's unchanged, so there's no change with the Fortran infrastructure. So I'll say a little bit more about that. So the C++ supports C++ 17, so the default is C++ 14. I think the C support is C11, and then there's kind of C11 plus GNU extensions that make up C17. And Fortran supports most of Fortran 2018, and I'll talk about that in the second section of this webinar. The environment is compatible with GCC 8.1. So you've probably noticed that major changes in Cray compiler come with a compatibility against a particular GCC toolset version. So these compilers come with compatibility against GCC 8.1, but the environment actually provides a GCC 8.3 as the actual compiler that you can use if you load prog-env GNU. There is one change with the C compilers, is that OpenMP is disabled by default. But the OpenMP implementation has been improved, so it supports some OpenMP 5 features. It's really OpenMP 4.5. And you just use, even though the infrastructure has changed to be Clang-based for C, you use the normal drivers and man pages, and you'll just see different options. So if you do man Cray CC under lowercase or Cray CC in uppercase for the CC part, you'll see the new command line options. But just be aware that the command line flags change here, so you'd have to change make files. And as a helper, if you use OFAST in Clang, you get a similar optimization to the default in the Cray C compiler, which already had optimization turned on. And for example, with the OpenMP, the options are different. So traditionally, you use -f OpenMP for a C-based compiler. Sorry, FOMP, but that's changed to FOpenMP for the Clang-based compiler. So I think that's quite a major change if you're a C user, and particularly compatibility of libraries there would be important. Okay, so now although the developer team has moved to using Clang, that means they lost a whole load of things. So they had to go back and put in a whole load of Cray features that people were used to from the Cray C and C++ compilers. So some of these relate to the front end and some relate to optimization. So some of these features encompass things like loop mark. So this is the listing that you can get from a Cray compiler that describes, for example, how a loop's been vectorized. Has it been unrolled? Has it been vectorized, for example? Decompilation, where you can get a low-level view of your application and how it's, some kind of intermediate representation. It's not really an IR, but it's something that compiler people understand. UPC support has been added back in, enhanced assembly listings, and then support for the performance tool, so that the right wrappers are placed in when you can compile with the performance tool module loaded. And specific performance improvements means adding things into the optimizer. Now, one thing that's not being taken up is the Clang implementation for the OpenMP runtime. So that is a Cray implementation, and there's a lightweight wrapper between the two, so that you can mix Clang OpenMP with Cray OpenMP. But this is something that's been developed by the Cray developers. And in alpha support is support for the OpenMP 4.5 directives that allow you to to program to NVIDIA GPUs. Okay, so I'll stop there just in case there's a question on that piece, because I'm going to switch to talking about Fortran next.
Yes, there's one question that's just come in asking why Clang?
Well, I don't know the answer to the question, so I'm going to guess. But I noticed that the C world is very much driven by compatibility. If you have your own compiler and the arguments are different, particularly in the driver, that causes no end of pain with interfacing with things like CMake. So I think a lot of it is to do with compatibility. And I have a suspicion that the licensing of Clang is relevant as well. But that is not in any way a Cray/HPE approved answer to that question. That's my guess as to what the answer would be. And the people I've mentioned this to seem quite happy, so they quite like the idea. So that I'm not really a C++ programmer, so I imagine there are some benefits to people.
Yep, the reply to that is thanks, Harvey.
Okay, so I'll carry on, but be happy to store up questions for the end. Or if I say something someone says is wrong, just interrupt me, Claire. Okay, so I'll now talk really about Fortran. So the current Fortran standard is Fortran 2018, and it was called Fortran 2015, but in the history of Fortran standards, the dates are meaningless, right? The date is a date you don't achieve usually, so they renamed it to 2018. So I'm going to talk about some of the features that are now available in the CCE 9 compiler, both in text form, so I'll say what the features are, but I've got some examples that will illustrate the features so to make it a bit easier than just going through the reams of text. And I'm specifically talking about the support in the Cray CCE compiler. Okay, so if we look at the history of Fortran, we started in 1954 with punch cards, and the really old days, and we went to Fortran 77, and we thought it was really good because it was a proper standard. And then Fortran 90, we got array syntax, and then it was improved in 95. We got Fortran 2003, and notice the dates lag the standards a little bit. And then the last compiler I went back to was the Cray version 7 compiler that brought in Fortran 2003 support in 2008. So there's a lag between the name of the standard and when it's standardized and when the compilers become available. So for Fortran 2008, essentially the support was there in CCE 8.1 in 2012. And currently we're almost there with Fortran 2018. So the target for the developers is to deliver that in 2020 with the CCE 10 compiler. Now I said that the current shipping compiler is a Series 9 compiler. It's actually 9.1.1. So we're getting there. We're getting close. So it's seen as a minor release, although you could argue that it's not really, because it includes 2 large technical specifications that were published before, but the features have been tweaked a little bit, so not identical to those. So you have a technical specification on interoperability of Fortran and C. You have a specification that relates to the additional parallel features in Fortran, so this is co-arrays, a range of other features, and many of these were already supported by various compilers. And if you want to see in real detail the precise differences, John Reed from the UK has been involved in Fortran standards for many, many, many years. He has a nice document that, for people really interested in this, describes the precise details of all the differences. So this is from the release notes from CCE 9, which was released in June. So essentially most of the features are there already, apart from a few things. So the things that are not there are support for teams. So this is where you have a group of images in a co-array application. So it's a bit like indicators in MPI. So that's not there. There are some issues with the intrinsics, which actually has improved, and I've got a slide on some of these things. There are some subtle things to do with allowing you to declare types in certain contexts, and one of those is for example, in data declarations. So these are smallish things. Locality clause for do concurrent. I don't have an example on that, but do concurrent allows you to say that a loop has no dependencies, a bit like IVDEP, right? But people argue about what IVDEP really means. So what a locality clause does is if you think of OpenMP scoping, where you can say things are shared or they're private, locality clauses are a similar idea. But they tell the compiler, for example, that your variable I inside some loop, not the index, some other I, is local to each loop iteration and is not the same I as the enclosing scope. So it allows you to say things like that. So basically useful for compilers to optimize the loop. So that's something that actually is there now and is in later release than 9. So 9.1 has this, but it didn't at the time of shipping. And then a whole raft of support for IEEE changes. So there was a new IEEE standard. We'd been a standard called IEEE, I think 754, don't remember the precise number, which defined the precise details of floating point arithmetic. And that had been updated, and the Fortran standard wasn't really taking account of that. So there are a range of features there, and some of those are not yet implemented. There's syntax for when you access an image. Should an image fail, you can get a stat variable back, and some of those are not yet implemented. There's a document that describes these things. So if you look at pubs.cray.com, you can go to a document that describes these features and the ones that are not there. So if I start with, and I'll go back a bit. So I've got a few little sections here. First one is talking about one of those major features I mentioned, which is interoperability with C. Okay. So this, if you remember the old days where you guessed how many underscores you needed, and you guessed whether you needed uppercase or lowercase, and you guessed whether you had to put the length of a character string when you passed it from Fortran to C. So this was improved greatly in Fortran 2003. So Fortran 2003 gave us interoperable types between Fortran and C. It gave us the ability to interoperate with functions and subroutines. It gave us the ability to reference global data from C. So for example, data in a module. It gave us the ability to pass both by reference, which was the only thing you could do traditionally, and by value, to match by value semantics of C. And it gave you the ability to associate Fortran pointers with memory in C, so with a C pointer target. And Fortran 2008 really didn't add much to this because of the work that was going on in those technical specifications. So it really added just a size of function. Now, it's true to say that many of these interoperability features were driven by the requirement to have a decent interface to MPI. So MPI traditionally really didn't have a Fortran-centric interface at all. So to do that properly using the nice features of Fortran was something that's been a desire for many people for a long time. And that's driven a lot of this standard work in this area. And I think the other thing is that the major thing that's been added that came from this technical specification is the ability to describe a Fortran object as an actual object. So historically, when you pass data between Fortran and C, you essentially passed a pointer. Now you can pass a type in C, which describes the thing that's being passed, right? So essentially you get an object, and this allows you to capture what was the type of the argument that came from Fortran. How big were its elements? What shape was it? Was it a two-dimensional thing? Was it a one-dimensional thing? Was it a scalar? And what layout was it? Now, the layout thing is extremely important because objects passed from Fortran don't have to be contiguous, right? So if you imagine an array section, it's not necessarily contiguous. And there was no way to deal with that in C, but now there is a way to do that. And I've got an example that will describe some of this. So you also have the ability to create such a descriptor so that you can pass an array, back into Fortran. And some other things that become useful, and again was motivated by MPI, was the ability to pass an argument of any rank into C. So there's a new concept of assumed rank dummy arguments. And they can be used in Fortran as well as C. So I've got an example to describe that. Similarly, it's nice if you can pass any type as an actual argument and declare that in the dummy argument. So this avoids you having to write interfaces to C where you write a routine for every single possible type of the actual argument. Support for optional arguments as well. So traditionally there was no way to say when you had an interface to C that some of those Fortran arguments were optional. Now the way that's handled now is that if an argument's missing, it maps to a null pointer. And of course, this can't be a value argument. It has to be one passed by reference, but that's really not a big deal. You can also allow C to use Fortran subscript expressions. So there's a helper routine that helps you do that. And then the other thing that came about because of the experience from MPI is the ability to tell a Fortran compiler about the situations where a Fortran variable might change out width of the scope of Fortran. So this originally was driven by asynchronous I/O, but it's relevant for doing non-blocking communication in MPI. So you now have a nice way to say, okay, this MPI routine is going to do something weird with your Fortran variables at times you don't understand. So there's a way to explain that in the Fortran code. So I have an example of this as well. So as I said, some of these slides are list-based in features, but we've got little examples to make it a bit clearer. So here's the first example. So in this example, if you look down to the program, so the program is calling, it's declaring an array, a real array R with dimensions 3, 100, and 100, and it's passing that array into a C routine. So it wants to pass into a C routine, which means we have to create an interface to describe the interface between Fortran and C. And that interface, which is the code above, is saying, okay, so I have a subroutine called describe. It has a binding to C language, and the C routine is called describe. So the name equals describe is really redundant here, but you could change the name at this point. It's using some helper information from an ISO-C binding module. In fact, it's not really required here, I don't think. And then the crucial piece is where we say type star. So we're saying any type can be passed through that interface. I'm not having to say real or integer here. The dimension can be anything. So it's dimension dot dot, which is something you might not have seen in Fortran before. And intent in, so I'm going to pass it in but not return it. And the other thing to notice here is, notice I didn't pass in an array, I passed in a slice, something that was strided, right? So I've passed in all elements one, and sorry, the first element in the first dimension, and then all of the elements in the other dimension. So if you index through this n-dimensional thing, you're striding through that data in memory. You know, you've got strides of, I guess, 3 and 300 going on here. So this is something that can be handled in the interface to C. Now, whether you want to is another matter. You could make it contiguous on passing it if you needed to. So here's some matching C code, and I hope you can read this. So the crucial things are the purpley colored bits, which are the new features. So notice that the describe routine in C is using something called CFI_CDesc_T. And that was provided from a header file called ISO Fortran binding.h. And this is the object that describes the Fortran array or the Fortran scalar, whatever it is, right? And there are various components of that and some types that help you with this. So there's a type that helps you declare a rank, a type, an attribute, a dimension array. So here you notice I set the rank to be the descriptor, but the rank component of that descriptor. So I can inquire what the rank was. I can get an array of dimensions. I can get a type. I can print out some attributes. So attributes basically tell you whether the argument that was passed is a pointer or an allocator or neither of those things. So, and then I get lower bounds and extents, so I can find out how big are any of those dimensions. So notice that dim1 has components extent, lower bound, and upper bound. Sorry, extent and lower bound. So here I can say what was the extent in any dimension and what was the lower bound of the object that was passed from Fortran. And then at the end, I can get the element length, and I can get the base address. So this is the address of the first element of that object. So this is a dramatic improvement. And you'll notice, I think the current mpitches are using this kind of technique to decompose an argument that's passed to them to find out information about those arguments. So you know, things have moved on dramatically. So one of the other features I mentioned was select rank. So it's now possible to, in Fortran, is to pass an argument that can have any rank. So you notice the second line here, the integer array is declared to have any dimension. So it has assumed rank dimension. And I can't say A equals 0 in this code, right? Because I can't reference something that could have any dimension. So, you know, Fortran gives and takes away at the same time. It sometimes says, well, you can be a bit generic with types, or you can be generic with dimensions, as long as you tell me what you've got, you know. So, you know, it's a bit schizophrenic that way. So in this case, there's a new construct called select rank, where you can say, okay, in this piece of code, I'm going to tell you what the rank is, and then you do the right thing. So here I'm saying, I want to choose some code to be run if the rank is 2. So within the select rank construct, I can say rank brackets 2. And at that point, I can reference that thing as if it's got rank 2. So here this routine is trying to set the elements along the diagonal, and it's setting the rest of the elements to 0. So I can say A equals 0 here. I couldn't say it above because the rank wasn't known, and then I can loop through those elements in a do loop. Similarly, I can do the same thing for rank 0. I can loop through the diagonal of a 3-dimensional object, and if I want to, I can have a default.
Harvey, sorry. Can you hear me? Sorry, Andrew.
Yes, I can hear you. You're a bit quiet, but I can hear you.
So why doesn't that fail at compile times? The compile notices that you've got it as a dot dot, so it allows you to write any code, I guess. Is that
so the compiler knows that object could have been any rank, but at the point it needs to know what rank it is, you've told it. So So you've constrained the actual
runtime.
code
Okay.
that can reference
Yeah.
that rank. So where it says rank brackets 2, at that point in the code, I'm allowed to reference it as a two-dimensional object.
But if I put that statement under a rank 3, it would get confused, I guess, would it? Or
It would fail because it would say your ranks don't match
at runtime, I guess. Yeah.
at compile time.
Okay.
It would fail at compile time. Well, it should fail at compile time. Didn't try it, but I think it would fail.
But the previously,
because remember, you statically told the compiler that that code is only relevant for a rank 2A, right? So this would be the problem. If you
I see.
if
Okay,
you
well,
wanted to support this for any rank, but you hadn't had the select rank statement, the compiler would really not know what to do. It wouldn't know the dimensions of the objects involved, and it would have to do so much checking. It would be too expensive. But here you've constrained the code that references, you know, an array when it had a particular rank. If that's right. If that's right phraseology.
Okay.
See what I mean?
Yeah.
It's a bit like when you use classes and types, where you say what the type actually was when you wanted to use it.
Oh, so that's a special select.
Yeah, that's it says select rank. That's a
sorry.
special
I saw the select
that's
rank,
not,
but I didn't see that the subclauses were rank statements, not so they're okay.
Yeah, that select rank is special. That's not like a normal select statement.
Sorry, I thought it was a normal select where you just had an intrinsic which gave you the rank of A. It's a special select.
No, I see what you mean. Yeah, okay, it's a bit more special than just
okay.
just you choosing an integer. Yeah,
fine.
The compiler knows what you're trying to do here. And because there's another, it could have been more obvious, but if you put rank bracket star, that means assumed size, which pretty much isn't used very often in Fortran nowadays. That's where you declare something as a bracket star. So you can put a star inside the brackets of the rank selection in this thing as well. But weird things happen when you use assumed size arrays, because the finite dimension gets an extent of -1, and the size becomes negative. It's a bit strange. Okay. So then the asynchronous attribute. So you might not have noticed, but Fortran introduced a block construct. So you can have block and end block, and you can declare variables there. But one thing you can do is you can give a variable an attribute. So here we're giving the variable buff an attribute. So that was a previously declared object. And we're saying, okay, within this block, that thing could change out with the scope of Fortran. So it's a way for you properly to handle non-blocking events. Okay, so the next one is to mention some of the co-array features that have changed. And I think the major one here is events. So historically, the idea of the co-array programming model was that you had a single-sided model. So you could essentially put data to another image, one of your executing processes or images in Fortran terminology, and you could get data just by using square bracket syntax. And those operations happened without the cooperation of the remote image. However, synchronization was essentially two-sided, right? So it was collective. So you either did sync images across all your images, or you did sync images across a subset of your images, or you did a kind of pairwise synchronization between images. But those things always had to match. Now, events are a way to do synchronization that's kind of split phase, so where you don't have to do that. So it allows you to be a bit more loosely synchronized. Okay. So here's an example, and I don't want to get hung up with the actual details of the code, but the blue piece of this is a kind of traditional halo swap. So on the right-hand side, you might not be able to see, but most of this is round bracket accesses, but the very right-hand side has square brackets. So the right-hand side is saying square bracket img pos 1 -1 comma img pos 2. So this is a co-array get of each edge of your array, given some, in this case, two-dimensional distribution of images. So you've got halo swap at the top, computation in the middle, and they've been bounded by a synchronization. So in this case, sync all, but it could have been something else. So that's what these events can change. So the idea of an event is that you cause an event to happen, and then you inquire whether it's happened afterwards. Okay, so the way you would declare that an event has happened is you post it. So you declare a special variable. So in this case, it's of type event type. It's been allocatable, and the variable's an array called ready. So ready is an array of objects. There's 4 of them because we've got 4 directions, and they're of type event type, and they're co-arrays. So to post an event, you just call event post on the variable, but on the remote image, right? So you're posting an event to another image saying I've done something, right? Essentially, I've got my Halo edge ready for you, right? So you send the event, you post the event, and then on the other side, you wait on the event. So this is a local operation. So image 1 could have posted an event to image 10, and then on image 10 we do a wait. So we sit there waiting, and then when ready 2 receives that event, we can carry on. So it's a way to split up all of that synchronization in a split phase way. And it's something that was really missing from the co-array programming model. And then you can just do the Halo swap, sorry, the computation as you would before, but we don't have the sync calls anymore. We just handled the synchronization with the events. Now, events actually do count, so you can test the actual value, but here we're not showing that. And you can also query an event rather than wait on it as well. So those are options. So that's a nice new feature. And Anton ran some tests, but he did them on nodes that were so small it was embarrassing. So he did see some advantage, but I keep asking him to do it on bigger scale, but he's too busy. So. Okay, so the next topic is just to mention that during the initial development of co-arrays and the standardization and the technical specification and Fortran 2018, some of the arguments to these intrinsics changed. So some of the arguments that you could apply to the co-sum, co-min, co-max. So this is collective operations for co-arrays, do a sum, do a minimum value, maximum value. The argument lists changed. And as released with the CCE9 compiler, you had to be careful which arguments you used, otherwise you get a compiler error. And that's now been resolved with CCE 9.1, so it's all fine. But just to mention that one thing that's not been implemented is the generic co-reduce, where you apply a function, but the other ones have been implemented. And it's a bit ironic because these things were supported in the Cray compiler so long ago. It's annoying that they were kind of became non-standard as the Fortran standards developed. But just to be aware of that bit of a gotcha. And there's been quite a lot of atomic routines added. So these are quite important because they give the ability to do a remote atomic update. And they also give the ability to do it on a special kind of variable that's declared with a special kind value. That means the implementation has the ability to do these atomics in the network hardware. So this is true of the Aries network on a Cray XC. If you do some of these atomics, they're actually done in the NIC. So the efficiency can be higher than doing them to the memory space of your application. So there are new atomics that kind of things like compare and swap atomics with fetch that have been implemented. Okay, so that's co-arrays, and then some random other features that we thought were just interesting. Okay, so implicit none's been enhanced so that you can say that external subroutines that you call now have no type, which means that you have to declare an interface for them. So that covers one other aspect of implicit none. The implicit none is originally defined applied to variable types, but not external routines. So if you say implicit none brackets external, then anything you call external either has to have an interface or has to be declared in an external statement. There are now more situations where you can reference a property of an object when you declare it. And I'll probably go quite quick over some of these because I've got examples, right? So the 0 format descriptor form, which automatically fills in the right number of characters, it makes your number as wide as it needs to be, has been extended. There's a way to have stop only print error messages in particular circumstances. There's now an error message argument you can apply if you want to find out what command your program was launched with and what environment variables there are. I'll explain about the out of range intrinsic in a second. And then there's a new intrinsic that is a generic reduce. So this existed for co-arrays, but there wasn't a standard one for arrays for people who like array syntax. So that's one of the things that's not been implemented in the CCE compiler. Oh, sorry, this is supported. It's the co-reduce that wasn't supported. Sorry, I got that wrong. And I think I've got an example of that one. So the other thing is co-shape. So this was requested, interestingly enough, requested by David Henty, who's on this call, because of an application that he had where this was quite useful to find out what are the dimensions in the code dimension space of a co-array, and enhancements to the random number generation. So you can now say whether you want random numbers that are different each time you execute your program, or more importantly, if you want random numbers that differ on each image. So this is a classic problem. You might not want a parallel application with 1,000 images all with the same sequence of random number. It's unusual that you'd want to do that. And then some small changes, like changes to how the way the complex and all, complex and intrinsics like all operate with extra dim arguments. And then hexadecimal IO. I have no idea why anyone wants this. I think it basically allows you to write out a number in hexadecimal form, because then you can completely represent that number. You can completely represent that mantissa without any conversion. So I don't know who wanted it, but someone must have wanted this. Okay, and then the other thing I mentioned, there's a whole range of IEEE features that allow you to do things like precisely match some of the modes defined by the latest IEEE standard. So these are things where you want to round to the nearest number, but which one do you get if they're equally far away? So the subtle things that people who really care about floating point operations would want to care about. Okay, so some examples. So I said you can reference a property of an object in a constant expression. So it's easier to show the examples than describe that. So in the first example here, notice how the integer b has been declared to be how many bits are in a type of that is an integer. So I want to know, I've got a variable b, how many bits can it contain? But I want to reference b when I do it. Okay. And it's the same with e. I want e to be square root of epsilon of the floating point model that my e is in, right? So I'm kind of referencing the object at the point I'm declaring it. And then similarly, I'm initializing an array of 10 elements here, but my implied do loop, I want to terminate it with 10, and just because I don't want to write 10 there, I can now say size of that object in one dimension. So I can, in those kinds of circumstances, I can do these things. And this just shows you the output if you want to print those. So this can actually be quite useful in situations that got really annoying where you couldn't do certain declarations before. Okay, so the edit descriptors, this is a thing that C's had since it was developed, and it was never been in Fortran, which is make something as wide as it needs to be. And that's what the 0 does. So that's been extended to cover more situations than before. It's extremely useful, to write I0, do it all the time. Okay, so error messaging, you can have a quiet argument to the stop. So you can now, and also the message can be a variable. So you can print out stop messages, but decide based on some logical expression whether you do it or not. And this example is a bit backwards, so it's hard to get your head around it. But if you have some message level, you can say, okay, if I'm above some message level, then print out the messages, or don't otherwise. But it'd be nice if it was allow, because then you wouldn't have to negate the expression. Okay, so out of range. So this is an intrinsic that tells you, should you want to convert a real to an integer, can it be done, right? Or would you be out of the range of the integer? So here's an example where I've declared a real with actually a supported kind value. That means it's got 128 bits. So I've declared a real of R128, and I set it to be the exponent of sine of some number, right? So that's clearly bounded to not be very big. So that's fine. So I get false from this result because 0.6691 can be converted to an integer and rounded to the nearest one. However, if I do e to the power of 1,000 times that, sorry, e to the power of 10,000, that's a big number. And that can't be represented by the integer. So the result is true here. It is out of range. So it's a way that you can check in advance whether conversions will work or not. Okay, so I mentioned the reduce. So here, reduce function that takes an array argument with a mask. You can define an identity operation, and the argument here, so the operation equals add, that's actually a subroutine. Sorry, it's a function, not a subroutine. So it's a function that takes 2 arguments and returns the combination, right? So in this case, it's adding them together. So that's a new feature. Okay, co-shape, as I mentioned. So in this case, we have a co-array declared with code dimensions 2 star. If I ran that on 16 processes, so I get 16 images, then I print this out, I get 2,8. And that can be quite useful in some examples when you want to know the actual arrangement of those things. Okay, and then I mentioned some quite esoteric IEEE routines. So here's an example of some of the different modes when you round. So you might want to round to the nearest value up, down, or the nearest one. And these are things defined by this new IEEE standard. So they're intrinsic, the support to do this kind of thing. I guess if you write a numeric library and you want to really, really be precise and meet that standard, then this is a way to do it. Okay, and then I think we're nearly at the end. So other features not yet supported. IEEE renamed what used to be called denormal numbers as subnormal. So there's been a change purely for terminology. The Cray hardware tends to not do this, so it tends to flush subnormal values to 0 anyway. So these are numbers that, if you remember what a floating point value is, so a floating point value is a mantissa and an exponent, and that's a bit pattern. So there are situations where you can essentially extend your range by using less and less bits of the mantissa and not scaling it for really small numbers. And so this is what that's about. And we're at the end. So if you really want to learn more about these compilers in general, and look forward to what the latest compilation environment is, the pubs.cray.com site has documentation on these. So I hope this has been useful. I mean, like I said, my intention was to give you a feel for how the environment might get to be different. If you move to another Cray system that's got a slightly different programming environment because it has a newer OS and a newer PE installed, or the things you're likely to see when ARCHER2 comes. So that's it, Claire, if you want to tell me if there are any questions.
So Harvey, I had a quick question about that denormal stuff.
Yeah.
You say Cray hardware doesn't support denormal, but there's not really any, isn't that an Intel CPU or an AMD CPU statement rather than to do with Cray? I didn't quite understand that.
Oh, you mean does the processors do it?
Yeah.
I'm not sure. I know that the documentation for the compiler says that, or the compiler team rather, when I asked them, said that the Fortran Standard doesn't require you to support that. So there's no onus on the compiler to support it. But it does have this flush to 0 option as well that you can choose not to set. So I'm not absolutely sure which circumstances that you might get those and might not get those.
The question was about
one of
the early
flush to 0 set as default, right? And it'll be slower if you turn it off.
Well, the earlier slides you were talking about passing non-contiguous array sections to
yes, that's right.
C. I didn't. So I lost a connection for a second. So you might have said this, but I didn't understand how from the Fortran side you knew that it wasn't doing a copy in, copy out to a contiguous section. Was that
because so it depends on how you've declared the interface. So if you said the interface was a C pointer, that then has to be a contiguous copy, right?
Okay.
However, if you use that assumed rank syntax, if you said type star dimension ... then you'll get that C descriptor will be passed. In which case you can use those special functions in your C program to decode what that descriptor had in it, and you'll be able to tell by decoding it that it's not contiguous. In fact, there is a function called isContiguous that you can apply to the descriptor to find out if it's contiguous. Okay. Now there's one subtlety that I didn't mention, which is when you declare the, let me see if I go back. So at this point, so see how it says type star dimension ... that means you'll get a descriptor. If that said type bracket C pointer, you won't. But you can at this point say comma contiguous as an attribute, and then Fortran will guarantee that what's passed is contiguous. Right, so you can force it to be contiguous. But as on this slide, so if you go through this, you can actually decode that descriptor to work out if it's contiguous or not by traversing it. At the same time, there is an isContiguous function you can apply to it to find out if that's true.
Maybe my Fortran terminology isn't up to scratch, but if you...
So bear in mind, this is not contiguous, this call, because that object's an array slice, right?
Yeah, but
if it had been : : 1, it's contiguous.
Yeah, but if you'd called if describe had been a Fortran routine, the compiler could have chosen to do copy in, copy out.
Yeah, so it all depends, but usually it depends on the interface, right? So if you're calling Fortran and you said dimension star and you made it assumed shape, it's going to have to copy it into something that's contiguous. So even in Fortran, you had situations where things were contiguous or not, or they may or may not be pointers and they may not be allocatable, but the rules generally force you to declare the interface in circumstances where it matters.
Right.
So that it knows what to do.
I thought that I thought that even with an interface, when the compiler could in principle pass a non-contiguous section, it was allowed to do copy in, copy out, but maybe I'm wrong. Maybe that's not true. I knew it would pass an array descriptor, so you could do array inquiries. So I didn't really understand being passing an array descriptor, which allows you to do things like size of, or it's not size of size, normal kind of.
That's what you mean.
Versus,
I think it depends on the context, really.
It is it's just because in MPI there's some weird inquiry functions. Does MPI Fortran respect asynchronous contiguous?
I see. Stuff. Okay.
Anyway, I need to look it up.
I was looking at the mpich code funny enough yesterday, and it is using some of these new features. It looks quite good. So can I just mention, Claire, that I don't know if I'm going to publish these slides, but if anyone emails me, if you know how to, or you mail the help desk, I'm happy to send you the talk if you're an Archer user. It's just I have one slide that's a bit problematic because it mentions future support for something, which, you know, is a tricky thing.
Okay, well, I'd like to very much thank Harvey for his talk this afternoon. We will, as usual, be putting this webinar up onto our training YouTube channel. And if anyone does come up with further questions, as always, you can mail in your question to the Archer Help Desk and we can pass that on to Harvey.
No problem.
Thank you very much to everyone for attending. Thank you to Harvey for a very informative presentation, and goodbye for now.
Bye.